just my good friend Morgan commented yesterday that there's kind of this piece that looked kind of tricky. Didn't we have something yesterday like 3k squared plus 5k plus 2?
Yeah.
Well, I got an x in there. That's no good. 3k squared plus 5k plus... Okay, come on, Kevin. 3k squared plus 5k plus 2. Good. All right. You get used to writing x all the time, don't you? Do you wonder why it's x? So, I mean, when you say 2x plus 1 is equal to 3, what it really means is 2 times what, right? It's like that thing, 2 times that thing, like what is that thing? And when algebra first started, they had a symbol for that thing, and it kind of looked like something like an X. I don't know, but whatever that missing thing was, that's why we use X. I'll give you a little bit more of the history some other time, but yeah. Yeah, well, and so when you first learn multiplication, just understand that when you're like in elementary, the dot really looks like a period, right? And so when kids see 5 times 2, yeah, the X they may associate with a letter of the alphabet, but all of a sudden when you move to algebra, this could be somewhat confusing because is this equal to, say, 10x? 5 times 2 times x, you know what I mean? And so, so I think that's the reason why you see multiplication be replaced by the dot is so that it doesn't get confused with the x operation. I think that you should start your own branch of mathematics. Raise your hand if you think Lindsay should start her own branch of mathematics. Okay, all right. Not a lot of faith from Skinnis. He's not raising his hand. A little judgmental there. All right. Okay, so I just want to pick up with this piece because it kind of happened quickly at the end. But I just want to I want to focus on this piece right here. Everybody agrees if we multiply out k plus 1 squared, you get k plus 1 times k plus 1, which is k squared plus 2k plus 1, right? And so we all know that this piece here will be 3k squared plus 6k, won't it? It'll be a 6k plus 3, right? So watch, I'll write the 3k squared, and I know I have a 3k squared, right? And then I'm going to write the 6k, because I'm going to need a 6k, right? But you don't have 6k, you have just 5k. So if I put a 6k here, what else do I have to have in order to make a 5k? A minus k. So I haven't changed the value of the expression at all, have I? And then you can see that here you're going to need a 3 times 1, which is a 3. So you're going to need a plus 3 here. But you only have a 2. So if I have a plus 3, I'm going to need a minus 1. So all we did in this step right here, all we did was take this 5k and separate it into a 6k and a negative k. And I know you haven't done that before, but that's an okay step to make use of. And you'll do that more in mathematics as you get to higher levels. And this 2 then we separated to positive 3 and a negative 1. And there's nothing wrong with that. And what's just super beautiful is as you do that, you can see you get this piece right here, but then you have the minus k minus 1. And there you have it. So this factors to 3 times k squared plus 2k plus 1 minus, and here I factor a negative 1 and I get k plus 1 all over 2. And then obviously this factors to 3 times k plus 1 quantity squared minus k plus 1 all over 2. And there we have it. So my goal today would be to do one together and then have you guys try one on your own. Like all on your own, see if you get the whole thing right. Can we do it? Want to try? Lindsay says, yeah. Ready, Linz? Yeah. Okay. Let's move to ones that are just slightly more difficult. Okay? Nope, you're ready. Trust me. Trust me, you're ready. Yeah. This is the big question. Do you trust Mr. Gentz?
Yeah.
Okay, then don't worry. Everybody in years past have been fine so long as they've shown up. It's the ones who say, I'm going to go to the beach instead, Mr. Gentz.
It needs a big upgrade.
Okay. Let's start here. And I want you to know that for some of you, I know you're seeing this, you're like, I don't see any point to this piece at all. And there's others of you who are saying, yeah, I don't really see any point to it, but I kind of get it a little bit, and I think it's okay. But every once in a while, there's those students as well that say, like, this connects with me in a way that I haven't had other mathematics connect with me. And before you judge that too much, that's where I was at. When I started to see this stuff, this is when I fell in love with mathematics. It was when I started to see the theory and the proof and the abstract, and I said, this is where I am at home. And you guys all have that, right? For some of you, it's saxophone performance, right? And for others of you, it's Spanish. And for others of you, it's softball. And for others of you, it's whatever. But everybody's made differently, and so we celebrate this piece too. So let's do this one. First, let's understand it. Can somebody help me expand this? Expand. What does it mean? Expand this. Yep. So 1 plus 4 plus 9 plus 16 plus ... What is the last thing that you plug in? N, and you get n squared is equal to n times 2n plus 1 times n plus 1 divided by 6. So somebody comes to you and says, what is the sum of the first 10 perfect squares? You're like, I have no idea. Well, the sum of the first 10 perfect squares, it turns out it's 10 times 21 times 11 divided by 6, whatever that is. That's how it works out. Perfectly, every time. What is the sum of the perfect squares? We're going to try to prove that it's that. Now, part of you is wondering, where does this take you? It's because of this that we could do something absolutely amazing in calculus. We can add up the area of an infinite number of rectangles, which absolutely changed the world forever in our ability to do math. I mean, it was incredible. And you'll do it next year. The first year I taught calculus, they hadn't ever seen this before, so we got to that section of calculus. I said, okay, you remember how you did math induction when you were juniors and stuff? And they're like, no, I don't think we ever did. And I said, oh, no! So we had to stop. We had to insert this for like 4 days. That was a long unit. Let's do it. What's my first step? Awesome. Let's do it. Show the rule holds true for the first few cases. Sweet. Let's start with case 1. What? Is that true? Oh, yay! Let me guess.
Okay, right.
Oh, no way. You'll be back, trust me. It'll be coming soon. Okay. It works for case 1. So what do I write for case 2? 1 plus 4. Now we're going to add up the first 2 perfect squares. And what does 1 plus 4 add up to? 5. What do I plug in for n? Do I plug in 1 or 4 or 2 for n? 2, because it's the second case. We've added up 2 things. Got that now? See how confused you were 3 days ago and how it started to become a little bit more clear? 2 times 4 plus 1 times 2 plus 1, or 3, divided by 6. Ooh, I kind of like that. See, the 2 times the 3 is the 6, and that cancels. I have the 4 plus 1 right there. Isn't that nice? 5, I'm not convinced. I'm doing case 3. Some of you are convinced that you could stop with case 2. You'd be like, you know what, I'm good. What do I do for case 3? Ooh, and I learned that back in 2nd grade. 1 plus 4 plus 9 gave me 14. Let's see if we get that. What do we plug in for n? 3. 3 times, what is that going to be? 6 plus 1 times 4 divided by 6. Let's see, 3 times 4 is 12, divided by 6 is 2, and 2 times 7 is 14. Hey, it all checks out, doesn't it? Isn't that awesome? I bet it works for every single number in existence. We could try to show it for every single number in existence, but that would require that we would live for eternity and do math all of eternity all the time. So, let's choose a different option. Let us prove by induction. We've done the first step. The second step is awesome and easy and beautiful. It says, not everybody at once.
Assume it holds true for k, n equals k.
And in that situation, you write down the same thing that we expanded up above, except instead of using n's, you use k. That's all it is. So we say 1 plus 4 plus 9 plus ... plus what? K squared is equal to? Nice. Oh, sorry. What is that called? The inductive hypothesis. You just sound so smart when you say that. Like,
I didn't know that was actually called. I actually write that.
no, you don't.
But I make them.
Oh, yeah. The third step is to show the rule holds true for case what? What is k plus 1? It's the next term. Ooh, now we've got to expand this out. You take 30 seconds, see if you can expand out what the k plus 1 thing will look like.
I don't like that.
That's okay, you don't have to like it.
Okay. Anybody else?
It's like dishes, for example. I don't like doing dishes, but I do them anyway.
Yeah.
It's important. It helps keep my house clean. It's good. People appreciate it.
Everyone is happy.
All right, you should have 1 plus 4 plus 9 plus ... plus k squared plus k plus 1 quantity squared. Give yourself a little clap. Good job. Yep, you can clap for yourself. No judgment here. See if you got this part right. You should have k plus 1 in parentheses times, k plus 1 times 2 times k plus 1 plus 1 times k plus 1 plus 1. A lot of parentheses there, isn't there? Did you get it all there?
So 2 plus. Wait, what's the last one? K plus 1 plus.
K plus 1 plus 1. Hi. Yeah. Excellent question. So what I did is I took this guy and I put K plus 1 there. And then I took this thing and I put K plus 1 there. And then I took this thing and I put K plus 1 there. Wherever I saw a K, I put a parentheses K plus 1. You see it now? Excellent question. I love when you ask questions. I understand better where you're at. Any other question? Okay, then let's do it. Here you go. We've got this guy right here. I got to make the left side look like the right side. What do I put in the place of this? The inductive hypothesis. I place K times 2K plus 1 times K plus 1 over 6. And so to answer your question, Lindsay, some people say, well, do you have to write IH there? Sometimes in this step in proofs, you'll see people write by the IH, we were able to do that. So like your justification that you would have saying you're like your geometry 2-column proofs. Okay, but I think, that's enough. Okay, what else? What do I have to put now? Good. And that's supposed to be equal to that thing. We just have to make the right side look like the left side. It's just that in this situation, it looks a little bit messier, doesn't it? So you actually now understand all the inductive hypothesis and mathematical induction pieces. What you need practice with is the algebra. Because algebra is beautiful, right? Until we can't do it anymore. So I'm going to show you a cool trick to be able to work around the algebra. Are you ready? There's many ways to work through this. I'm going to give you the one that will work basically all the time for you, okay? Let's find common denominators. You good with that? So I'm going to multiply top and bottom by 6. Great. So I've got K times 2K plus 1 times K plus 1 plus 6 times K plus 1 quantity squared over 6. I'm having one of those moments where I kind of want to show you something that could maybe work easier. What do you want me to do? Do you want me to show you the surefire way that'll work all the time, or do you want me to show you something that's a little bit of a shortcut? Okay, here we go. That's the way I taught all the other classes. We'll go to. All right, so we got to now, we're going to have some terms that could combine here, right? So let's multiply this thing out. So 2K times K will give us, and then times a K will give us 2K cubed. Great. Well, so what I'm doing kind of 2 steps here. I'm trying to FOIL these out, Morgan, and then I'm going to multiply through by K. Then I'll have 2K and 1K, which will make times K, 3K squared. And then we'll have 1 times 1 times K. And we all know that when you take K plus 1 and multiply it out twice, you get K squared plus 2K plus 1, right? So if you multiply through by 6, what are you going to get? 6K squared plus 12K plus 6. All over 6. Okay, so somehow that thing is supposed to look like that thing. Well, at least we got the 6 in the bottom, huh? We don't have much else right now, but that's okay. All right. We can combine some like terms, can't we? 2K cubed plus 9K squared plus 13K plus 6 all over 6. Now, They're trying to tell us that factors to this. But I don't know about you guys, when I look at that, I don't see something that factors very well, do you? Fortunately for us, we know that one of the factors is k plus 1. Like, you know that, right? Do you remember what you could do if you know one of the factors? Find the other one. How? Chapter 3, first semester. RRT.
Or what?
Rational roots theorem. Right? And we just use our little synthetic division. Like, sure you do. Remember, if k plus 1 is a factor, then I can put a negative 1 there, right? And then what are the coefficients across the top? 2, 9, 13, and... No, we're going to make it super easy. Don't complain. This is actually really nice.
Kind of stressing me out.
No, drop the 2.
So does this like bubble look like? Can we put this into
I'm doing this on the side, so this is kind of, this wouldn't be real appropriate to put in a proof. People would say, oh, that's kind of messy. They look down on us in that situation. We want to keep our standing in the mathematical community. Okay, so multiply negative 1 times 2 is negative 2. I add and I get 7. And then negative 1 times 7 is negative 7. I add and I get 6. And I get negative 6, I get 0. It looks like it factors, doesn't it? 2, 7, and 6. So we have this factor. That's really nice. We've got k plus 1 times 2k squared plus 7k plus 6. That looks a little bit more like what we want, isn't it? Does the 2k squared plus 7k plus 6 factor? Yeah, let's factor that. We got k plus 1 times 2k and k what goes here? 6 and 1? Say plus 3 and plus 2? Are we okay with that? And we just peek on over to the right-hand side over here. I've got the k plus 1 on the end. Is that a k plus 2? Yeah. And is this a 2k plus 3? Yeah, I should just, in order to make it look like that, I should just separate the 3 into what? 2 and 1. Yeah, so let's just go like this. We're almost there. K plus 1 times 2k plus 2 plus 1 times k plus 1 plus 1. And then what do I have to factor out in order to make this look identical? The 2 out of that. So k plus 1 times 2 times k plus 1 plus 1 times k plus 1 plus 1 over 6. And that equals what we had above. That's a nice proof right there.
Would it be bad if like you know that it's gonna equal each other, so you just write that from the beginning?
You know, so the nature of the proof is to be able to follow each step and be able to see that you got exactly from there to there. And so you're right, it is tempting to just write it because you're like, okay, so I know it's going to work out, but you got to see it work out.
Okay.
And that's the nature of it. So it's kind of neat.
I forgot to show my work. I just fell on my head.
You know, the cool thing is that, you know, now that you guys have seen a couple of these examples, you could really choose whichever one you want. But right now, I think you should just try B on your own. And you can do it. Try it. See what happens.
That's what I've been doing.
Okay, so I'm going to kind of skip ahead here to 1 plus 4 plus 1 plus 8 plus 27 plus ... plus k cubed is equal to k squared times k plus 1 quantity squared over 4. Is that correct for your inductive hypothesis? And so then your step 3 should be show true. And we got all that. And so you'd have 1 plus 8 plus 27 plus ... plus k cubed plus k plus 1 quantity cubed is equal to k plus 1 quantity squared times k plus 1 quantity squared over 4. Okay, watch my little trick. So a lot of you got to that point where you're using synthetic division, making the right look like the left. Great work. That always works. Sometimes it takes a little while, but it always works. Can I show you a little trick? For this, I will put in its place k squared times k plus 1 squared all over 4. Are you okay with that? You then decided to find common denominators, right? And when you did that, you got k squared times k plus 1 squared plus 4 times k plus 1 cubed all over 4. Everybody should have that written down. Now, some of you said, well, I don't know if I really want to go through the work of multiplying that out. And depending on how good you are at factoring, you might not have to. Watch. It's really cool. I have 2 terms. I have that term, and I have that term. What do both of these terms share in common for a factor? K plus 1 squared, right? So watch. I'm going to factor out a k plus 1 squared. And when I do, what is left here? Just k squared. What's left here? See that? Now, why is that so attractive? Because, look, this k plus 1 squared, it's sitting right there. Now, all I'm trying to do is make this blue part look like that part right there, right? Well, that's not that big of a deal. We can do that real easy. We're just going to do k plus 1 quantity squared times, that's going to be k squared plus 4k plus 4. Whoops, sorry. Does k squared plus 4k plus 4 factor? To what? Yeah, k plus 2 squared. That's pretty close to what I want, isn't it? What do I have to do to make it look like what I want now? Split the 2 and the 1 and the 1, right? That little trick. So k plus 1 squared times k plus 1 plus 1, that quantity squared over 4. And all of a sudden, that's identical to what we had over there, and I'm done. Do you see that nice little tricky factoring technique I used with that taking out that common factor? That's a nice option as well. You know, part of what I like about this is it forces us to also review synthetic division, factoring, and other strong algebraic techniques. Nice job. Come tomorrow with your work, and you're going to have a wonderful assessment. Trust me.